A rule of thumb formula for residential and commercial applications is as follows: 4 kVA per horsepower of the largest motor, plus 1 kVA per additional horsepower. Considering the largest motor is 7 horsepower, and there are 3 additional motors, including a welder, lathe, and woodworking equipment, the total horsepower is 7 plus 3 equaling 10 horsepower. Using the formula, kVA equals 4 times 7 plus 1 times 3. This calculation results in a kVA of 31. Based on these calculations, a 31 kVA transformer would be a suitable size for this application. This should provide sufficient capacity to handle the combined load of the air compressor, welder, lathe, and woodworking equipment. However, there are other considerations. Motor inrush currents can significantly increase the transformer load temporarily. Motors can draw significantly higher currents during startup. If multiple motors are likely to operate simultaneously, consider a transformer with a higher kVA rating to provide ample headroom. He should also allow for future expansion of the electrical load by selecting a transformer with some additional capacity. Remember, this is just a rule of thumb formula and may not be accurate for all applications. It is always recommended to consult with a qualified electrician to determine the most appropriate transformer size. To further clarify the concept of transformer sizing, it's important to understand the relationship between kVA, volts, and amps. The kVA rating of a transformer essentially represents its power handling capability. It indicates the apparent power the transformer can deliver without exceeding its design limits. A formula to relate kVA, volts, and amps in a single-phase system is kVA equals volts times amps divided by 1000. In a three-phase system, the formula is kVA equals the square root of 3, which is approximately 1.732 times volts times amps divided by 1000. When sizing a transformer, it is crucial to consider the load characteristics. Different types of loads, such as resistive loads, inductive loads, and capacitive loads, have different power factor characteristics. The power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kVA. A lower power factor means that a larger kVA transformer is required to deliver the same amount of real power. For motor loads, it is generally recommended to assume a power factor of 0.8 for initial sizing calculations. This helps to account for the reactive power component associated with inductive loads. Motor starting, as mentioned earlier, is a critical factor in transformer sizing. When a motor starts, it draws a significantly higher current than its running current, typically 6 to 8 times the full load current. This inrush current can cause voltage dips and potentially overload the transformer if it is not properly sized. To mitigate the impact of motor starting, several techniques can be employed, such as reduced voltage starters, soft starters, and variable frequency drives. These devices gradually increase the voltage applied to the motor, reducing the inrush current. Another important consideration is the transformer's impedance. The impedance of a transformer is the opposition to the flow of alternating current and is expressed as a percentage of the transformer's kVA rating. A lower impedance transformer will typically provide better voltage regulation during motor starting, but it will also result in higher short-circuit currents. Selecting the appropriate transformer impedance is a trade-off between voltage regulation and short-circuit current levels. Furthermore, the ambient temperature and altitude at which the transformer will operate can affect its kVA rating. Transformers are typically designed to operate at a specific ambient temperature, such as 40 degrees Celsius. If the ambient temperature is higher than the design temperature, a transformer's kVA rating may need to be derated to prevent overheating. Similarly, at higher altitudes, the reduced air density can affect the transformer's cooling capacity, requiring derating. In addition to the load calculations and environmental factors, it is essential to comply with relevant electrical codes and standards when sizing a transformer. The National Electrical Code, or NEC, provides guidelines and requirements for transformer installations, including overcurrent protection, grounding, and ventilation. It's also important to check with local authorities and utility companies for any specific requirements or regulations that may apply in the area. When selecting a transformer, consider the available voltage levels and phase configurations. Transformers are available in various voltage ratings, such as 480 volts, 240 volts, 208 volts, and 120 volts. The primary voltage of the transformer should match the available supply voltage, and the secondary voltage should match the voltage requirements of the loads being served. Transformers can also be single-phase or three-phase, depending on the type of loads being supplied. Single-phase transformers are typically used for residential and light commercial applications, while three-phase transformers are used for industrial and larger commercial applications. The type of transformer enclosure is another factor to consider. Transformer enclosures are designed to protect the transformer from environmental conditions and to provide a safe working environment. Enclosures are classified based on their degree of protection against solid objects and liquids, as defined by NEMA, the National Electrical Manufacturers Association, standards. Common enclosure types include NEMA 1 for indoor use, NEMA 3R for outdoor use with rain protection, and NEMA 4 for watertight applications. Regular maintenance and inspection of transformers are crucial for ensuring their reliable operation and preventing failures. Maintenance activities may include checking the oil level and condition, inspecting the bushings and connections, and performing insulation resistance tests. It is also important to monitor the transformer's temperature and load levels to identify any potential problems early on. Another method used to determine the size of a transformer is by calculating the total connected load. This involves summing up the kVA ratings of all the individual loads that will be connected to the transformer. However, it is important to apply demand factors to account for the fact that not all loads will operate simultaneously at their full rated kVA. Demand factors are typically based on the type of load and the expected usage patterns. For example, lighting loads may have a demand factor of 1.0, while motor loads may have a demand factor of 0.8 or lower. After applying the demand factors, the total kVA demand is calculated, and the transformer is sized accordingly. In addition to kVA rating, transformers also have a kilovolt ampere reactive, or kVAR, rating, which indicates the amount of reactive power the transformer can handle. Reactive power is the power that is required to establish and maintain magnetic fields in inductive loads, such as motors and transformers. A higher kVAR rating is needed when serving a large number of inductive loads with low power factors. Power factor correction capacitors can be installed to improve the power factor and reduce the kVAR demand on the transformer. These capacitors provide reactive power locally, reducing the amount of reactive power that needs to be supplied by the transformer. Another type of transformer is an autotransformer, which has a single winding that serves as both the primary and secondary winding. Autotransformers are typically used for voltage step-up or step-down applications where the voltage ratio is relatively small. They are generally smaller and more efficient than two-winding transformers, but do not provide electrical isolation between the primary and secondary circuits. When installing a transformer, it is important to provide adequate ventilation to prevent overheating. Transformers generate heat as a result of core losses and winding losses. The heat must be dissipated to the surrounding air to maintain the transformer's operating temperature within its design limits. Ventilation can be provided by natural convection, forced air cooling, or liquid cooling. The amount of ventilation required depends on the transformer's kVA rating, the ambient temperature, and the enclosure type. Transformers also require overcurrent protection to protect against short circuits and overloads. Overcurrent protection can be provided by fuses or circuit breakers. The size of the overcurrent protection device should be selected based on the transformer's primary current rating and the applicable electrical codes and standards. It is also important to provide proper grounding for the transformer to ensure electrical safety. Grounding helps to prevent electrical shock hazards and provides a path for fault current to flow back to the source in the event of a ground fault. The grounding system should comply with the requirements of the NEC and other applicable standards. In addition to the above considerations, it is important to consult with a qualified electrical engineer or electrician to determine the most appropriate transformer size and configuration for a specific application. They can perform detailed load calculations, assess the site conditions, and ensure compliance with all applicable codes and standards. Remember that selecting the right transformer is a crucial step in ensuring the safe and reliable operation of an electrical system. A properly sized and installed transformer will provide years of trouble-free service. When dealing with multiple loads, diversity factor is important. Diversity factor is the ratio of the sum of the individual maximum demands of the various loads to the maximum demand of the entire group. It essentially acknowledges that not all loads will be operating at their peak demand simultaneously. Applying a diversity factor can reduce the overall transformer size requirement compared to simply summing the connected loads. For example, if you have several motors, each with a peak demand of 10 kVA, but they are unlikely to all operate at peak demand at the same time, you might apply a diversity factor of 0.8. This would mean you only need to account for 80% of the total connected load when sizing the transformer. Another aspect to consider is the voltage regulation provided by the transformer. Voltage regulation is the change in secondary voltage from no load to full load conditions expressed as a percentage. A lower percentage indicates better voltage regulation, meaning the secondary voltage will remain more stable under varying load conditions. Good voltage regulation is important for sensitive electronic equipment and can prevent malfunctions or damage. The type of core material used in the transformer also affects its performance. Common core materials include silicon steel and amorphous metal. Amorphous metal cores generally offer lower core losses and higher efficiency compared to silicon steel cores, but may be more expensive. The choice of core material depends on the specific application requirements and cost considerations. Transformer efficiency is another important factor to consider, especially for large installations. Efficiency is the ratio of output power to input power expressed as a percentage. A higher efficiency transformer will consume less energy and generate less heat, resulting in lower operating costs. Transformer efficiency is typically highest at around 50% to 75% of the rated load. Consider the type of cooling when dealing with a transformer. Transformers generate heat due to core unwinding losses, as discussed earlier. Different cooling methods are used to dissipate this heat and maintain the transformer's temperature within acceptable limits. Common cooling methods include natural air cooling, forced air cooling, and liquid immersion cooling. Natural air-cooled transformers rely on natural convection to dissipate heat and are typically used for smaller transformers. Forced air-cooled transformers use fans to circulate air over the transformer's core and windings, providing more effective cooling. Liquid immersion-cooled transformers immerse the core and windings in a dielectric liquid, such as mineral oil, which provides excellent cooling and insulation properties. Liquid-filled transformers often require regular maintenance to check the oil level and condition. You must also determine the proper wiring and connections of the transformer. Transformers have primary and secondary windings that must be properly connected to the power source and the load. The wiring connections should be made in accordance with the manufacturer's instructions and applicable electrical codes. It is important to ensure that the connections are tight and secure to prevent overheating and electrical faults. When connecting a three-phase transformer, it is important to pay attention to the phase sequence. Incorrect phase sequence can cause motors to run in the wrong direction and can damage equipment. The phase sequence can be checked using a phase rotation meter. In addition to the technical aspects of transformer sizing and installation, safety is paramount. Transformers operate at high voltages and can pose significant electrical hazards if not handled properly. Only qualified electrical personnel should work on transformers. Always de-energize the transformer and verify that it is not energized before performing any work. Use appropriate personal protective equipment such as insulated gloves and safety glasses. Follow all applicable safety procedures and electrical codes. Consider future load growth when selecting a transformer. It is always a good idea to select a transformer with some extra capacity to accommodate future load growth. This can save you the cost and inconvenience of replacing the transformer later on. A good rule of thumb is to add at least 25% to the calculated load to allow for future expansion. Consider the location and environment when selecting a transformer. The location where the transformer will be installed can affect its performance and lifespan. Factors to consider include ambient temperature, humidity, altitude, and exposure to corrosive substances. Choose a transformer that is suitable for the specific environmental conditions. For example, if the transformer will be installed in a damp or corrosive environment, choose a transformer with an M4 enclosure. The final step in transformer sizing is to verify your calculations with a qualified electrical engineer. Even if you have followed all of the above steps, it is always a good idea to have your calculations verified by a qualified electrical engineer. An engineer can review your calculations, assess the site conditions, and ensure that the transformer is properly sized and installed. This can help to prevent problems down the road and ensure the safe and reliable operation of your electrical system.